about fixed point properties.
Right. So I'd like to thank the organizers for inviting me to talk. Yeah. I will overview some fixed point properties on Banach spaces. It's not going to be exhaustive, just a few things. So let me remind a number of things, even if I'm sure you have seen them under various sources in previous talks. So I'm going to look at three equivalent definitions of property T that allow for natural generalizations in the setting of Banach spaces. Obviously, there are more than three definitions, but these three are sort of naturally inviting one to reformulate them in the setting of Banach spaces. So there's obviously the almost invariant implies invariant vectors one, the spectral gap one. This one is really very natural to generalize. Then there is the sister algebra one. This one is the one used by Vincent Laforgue to formulate the strongest version of the property T that I know, at least. So in this one, we look at the space of representations, of certain representations. Now, in the classical case, it's just the unitary representations over Hilbert spaces, and this is going to give a seminorm on the algebra of the group, and one considers an extension, and the condition is that this sister algebra would contain a centrally idempotent, which, whenever represented in one of those representations in your class, gives actually the projection onto the space of fixed vectors. And for instance, Vincent reformulated this for Banach spaces in a very large class and for representations that are uniformly bounded with a certain condition on the growth. And then the last one that appeared a lot before, in particular the previous talk, is the one in which we make the group act by isometries, like metric isometries, on a Hilbert space in the classical case. They automatically are defined by an old theorem of Mézard and Ulam. And the formulation is every action has a global fixed point. If the group is finitely generated, that's the definition. If the group has a topology, it's a topological group, you have to add continuous everywhere. There's a condition of continuity. And the third representation, the third definition also allows to formulate a strong negation of property T, which is also popular and implied a lot of things. Its initial name was the horror property, but it's also named atiminability for reasons that are going to become apparent. I think this terminology is due to Gromov. And, right. So I'll illustrate these generalizations and various things that can be said on two sets of examples. So the first one is really the classical one, and the one in which this whole story first appeared. It's the group of isometries of symmetric spaces, because actually Kazdan introduced property T to prove that certain lattices are finitely generated. I will only stick to symmetric spaces. I won't look onto p-adics on non-Archimedean, so I'll only look on this kind of things. And at least in this slide, just to simplify things, I will assume, so first of all, we're talking about symmetric spaces of non-compact type. So that means sectional curvature non-positive and also no Euclidean factors. And just to simplify things, I'm also going to assume that it is, the space is irreducible. So we don't have direct products. And then we're looking at the group of isometries, the connected component of the identity of the group of isometries of the symmetric space. This is a Lie group. And then we look at its lattices, that is discrete subgroups, such that the quotient has a finite measure induced by the higher measure, or equivalently such that the quotient of X by G has finite volume. And then the picture is as follows. The sort of the line between atiminable and property T goes through the middle of the rank 1 symmetric spaces. So for symmetric spaces over the reals or over the complex numbers, the group of isometries and the lattices are atiminable. While for the case of the hyperbolic case over the quaternions, or for the field over the for the plane over the octonions, the group of isometries and the lattices are property T. And in higher rank, it's both the Lie group and its lattices have property T. And the general belief is that, and actually illustrated by a lot of results by now, is that the property T of in higher rank is more robust, in the sense that whenever, for all the known strengthenings, as even the previous talk showed, it's always the case that the higher rank lattices preserve that stronger version, while the rank 1 case fails to have it. Right, now going back to property T and determinability. So as I said, this was the first set of examples, and actually in a way, it's where the story began. Now going back to amenable groups, there are other examples. So first of all, amenable groups are amenable, which explains the terminology. So actually terminology means it's a generalization of amenable and it is a negation of T. And that's how Prof justified this. Then also, not only lattices of isometries of the real or of a complex hyperbolic space, but merely groups that act properly. So any group that acts properly on a real or on a complex hyperbolic space is amenable, in particular free groups. And that already shows that beside amenable groups, amenable groups contain a lot of things that are very far from amenable. And okay, and now here comes the second source of examples, and I'll come back with details for this one, random groups. So there are various models of random groups, but in all the models, if one adjusts the model such that there are comparatively few relations compared to the how many one can have, then the generic property is amenability, while if we have many relations, that the generic property is property T. And both are obviously advertisements for both properties. So that means that if you adjust your notion of what generic is, it will be either one or the other. So I'm going a bit fast because I know that there are a lot of experts in the room on all these things. On the other hand, if you want me to stop and explain anything, please just stop me. Because otherwise I'm going to go faster and faster until it will become unbearable. So, yeah. No, I'm not, but I might because I drank out of it. Okay. So now let's move on to what I mentioned before, and again, it was already apparent in quite a number of presentations. We want to look at versions of these two properties when we replace Hilbert by Banach. And the most natural thing is to look at LP spaces. And what is interesting is that Gromov already stated this as a problem. So I actually worked on this for a while until I realized that this was also an asymptotic invariance. So he stated it in this section. He suggested as a problem that one should study actions on LP spaces in connection with property T and determinability. So obviously that's been a while ago, like 30-something years ago, and meanwhile this has been done quite well, but not completely covered. And now if we go to the three equivalent definitions, the almost invariant implies invariant, the C-star algebra, and the affine one. Interestingly, so the first one, the almost invariant implies invariant, doesn't give you anything new. So if you replace Hilbert by any LP space, you just get something equivalent to property T. So this follows from work of Bader, Fuhrman, Gelander, and Monod. And the same thing happens for the C-star algebra, only now it's going to be a group algebra because it's not going to be a C-star. But otherwise, the same thing is true. Asking for the existence of an idempotent with those properties for an LP instead of Hilbert is just going to give you back property T. So those two are not interesting extension to move to LP. But funnily enough, the third one does give you an interesting strengthening, actually, of property T, which also shows, actually, that the equivalence of the three is going to fail as soon as we move beyond the world of Hilbert spaces. So up to now, I guess all is clear. If you don't have questions, I have a question for you. If you know what is if there is a reference for this. I mean, I would say it doesn't appear explicitly, this one. Doesn't appear explicitly in this paper. I mean, I know how to deduce it actually. But I mean, if it does appear explicitly in another paper, I'm happy to add that as a reference. Otherwise, it's just...
Is your paper with Novak, no?
Well, yes, but I mean, we do this in the paper with Novak, but I have the feeling that this must be something older. Yeah, I mean, in the paper with Piotr, we basically produce because spectral gap means that the Markov operator is contraction, and then by iterating, by considering powers of that, you just get the idempotent in the limit. So that's how you get it. But I'm quite sure that this must have been known before. Anyway, so what happens for the third definition? Well, what did I do? I did something. Oh, right. Something is not.
Sorry, since you insist.
Yes.
I don't understand what's written after the Bader-Furman-Gallender-Monod, the reformulation of the spectral gap.
So the almost invariant implied
like
invariant
100?
definition. Sorry?
So you fix P like 100, and
You
you're saying
fix a
that
P,
spectral gap is going to
and
give
you require that you have a spectral gap for representations only on that LP space. And that's going to give you back property T. It's equivalent to property T for your favorite. Right. So, we're talking now again about actions by affine isometries on LP spaces. And then the two like equivalent properties would be every action on an LP space has a global fixed point. And at the opposite end, we have there exists a proper action by affine isometries on an LP space. That's the property. Right, so why is that interesting? Well, I mean, obviously it's quite a natural thing to do. For instance, I'm anticipating here a little bit because I'm about to say that for P large, FLP is a stronger property, is a stronger rigidity property, so it implies T but is strictly stronger. And therefore, various rigidity results hold for groups having the FLP property with under weaker conditions. For instance, Navas, he has some rigidity result if you represent the group by diffeomorphisms over the circle, and for property P, you have a certain condition of smoothness, and T, and for FLP, the condition of smoothness can be weaker. And the other, I mean, for 18 inability is that this is already true for 18 inability. So Baum-Kohn, the classical Baum-Kohn is true. It's Hickson and Kasparov, and therefore Novikov. And for the LP version, one has Novikov. It's a result by Kasparov and Yu. So they're also interesting as properties. And they're also interesting as strengthenings for FLP, respectively weakenings for AT, as the next, it will be apparent in the next slide. Right. So what we know is that we can fix any P, and the fixed point property is going to imply T. Before I mentioned only the property for 1 to infinity, it can be extended for 0 to 1 if we agree that in this case we're only asking for bounded orbits. So for P larger than 1, bounded orbits is equivalent to fixed point because of the uniform convexity. So if you have a bounded orbit, we just consider the minimal sphere containing it and the center is fixed. For P equal to 1, it's already tricky, and I will say more. And between 0 and 1, we fail to have this. So we just have to assume bounded orbits. But other than that, this FLP always implies T. And it is equivalent to T between 0 and 2 again. With this caveat that between 0 and 1 it's bounded orbits. It follows from the Lorman-Guichardet. So they reformulate T in terms of conditional negative definite kernels, and the P norm power P turns out to be conditional negative definite kernel. And for P equal to 1, as I said, if we consider the formulation bounded orbits, then the equivalence follows from all results. The fixed point seems to be strictly stronger, but in fact, it is equivalent to T and to bounded orbits, but it requires work, so it's a theorem of Badea-Galander-Ramonov. For P larger than 10, we know that it is strictly stronger. And again, I mean, if you know what happens between 2 and 10, please tell me, because that's the best that I know. So why can we say that? Because of work of Pierre Pensieux and of Cornelia Drutu, who showed that already the group of isometry, the full group of isometries of the quaternionic, any quaternionic hyperbolic space, a group with property T starts acting properly and continuously if it's Lie, if we consider P larger than the conformal dimension of the boundary. So the conformal dimension of the boundary, you have two super experts in the room, Pierre and John, okay? It is the minimal Hausdorff dimension among all the metrics on the boundary that are quasi-conformal to the visual world. And it has a lot of interesting properties, but again, I mean, better people than me can tell you things about that. And as it happens, the same thing is true for hyperbolic groups. So every non-elementary hyperbolic group, well, if it's elementary, then you don't need to bother. But if it is non-elementary, then again, as soon as you go above the conformal dimension of the boundary of that group, G acts properly on that LP space. And between 2 and 10, there's nothing known, at least not by me. Please let me know if you know otherwise. What is also known, and for this I should attribute to Fisher and Margulis, one can always go a little bit beyond 2. So every group with property T also have the fixed point property for a P a bit larger than 2, but the epsilon here, it depends on the group. Actually, this will become more clear later as I move on with this kind of property. And, well, as announced before, if we look at higher rank lattices, they have all the fixed point properties between 0 and infinity. So that's a result of Badea-Furman-Galander-Ramonov. So this is how things stand. If we just look at affine actions by isometries on LP spaces and the fixed point properties, respectively, bounded orbits in that case. So that gives one the idea that a first way to measure the strength of the property T of a group, which has property T, obviously, would be to look at the entire range of fixed point properties. So we look at all the P between 0 and infinity, such that G has this fixed point property. Well, obviously, if you want it to be non-empty, you already have to assume T. Because of what I just said before. If you have an FLP property, that already implies T, and T already brings with it the entire interval 0, 2. So it's either empty or it contains the interval 0, 2, and actually, as mentioned before by Fisher-Margulis, it goes a little bit beyond 2. So this is, let's say, a first way of measuring the strength of property T for a certain group. And what can be said about that? Well, first of all, it is an open set. So this was already, in fact, it's the argument a little bit already in the argument of Fisher-Margulis. It's also in our book, but the truth is it needs 2 ingredients, and it's more general than that. All the fixed point properties are open, provided that you consider them on a class of metric spaces that is closed with respect to ultra limits. So it's just, it uses an argument of Gromov that appears in random walks in random groups, I believe, that, and just an argument of ultra limits. So it's really not difficult, which is why it appeared in a book. Oh, sorry. And the second follows from a theorem of Michael de la Salle and Amin el-Marakchi. It's actually an interval. So that, in fact, shows that what we really want to know is this parameter. This is going to measure the strength of the property T. Right, so maybe I should stop here and ask if there's any question. Okay. Right, so we said we have property T on one hand, we have amenability on the other, and as it turns out, there is something similar happening for amenability. We can play the same game, and it is successful up to a certain point. So here as well, we can consider the set of parameters such that the group acts properly on an LP space. And here too, we can use a theorem of Michael and Amin el-Marakchi to state that actually this is an interval as well. The only thing that is a bit frustrating, so maybe I should, yeah, okay, so we can say two things. One, we can deduce that it is an interval. The thing that we can't say is if it is an open interval or a closed interval, whence the question that I asked in the end. To my knowledge, this is still open. I mean the question, not the set. Because the proper actions don't behave well to limits, very obviously. Okay, and it follows from the work of Bourdon, in fact. So following on, I mean, like, yeah, that for hyperbolic groups, we can always say that we have a proper action above the dimension of the boundary, and therefore we have this inequality. We have this inequality. Right. So, so we have these two sort of sets, and in fact, two parameters. F of G, which measures how strong is property T for a certain group, and P of G, which measures the degree of amenability of that group. Now, if we look at just the first set of examples, the lattices, well, in that case, like, things are quite limited and clear. I mean, higher rank have all the fixed point properties, and therefore F of G does not exist. And for the rank one, that's pretty much all that we can say. Let me now explain that there is another source of groups where these questions are interesting, and actually they're sort of also, they have an interesting answer, and these are random groups. So there are two models for random groups. There is the Gromov density model and the triangular density model. They both require a density. And the idea is as follows. Both models are on finitely presented groups. There exists also a model on finitely generated groups. It's in the survey of Yann Olivier, but to my knowledge, nobody worked much with that one. And the idea in the triangular density model is the following. So I'm working with finitely presented groups. A priori, I mean just any set of relators, but then I can always change that as a presentation that is triangular, in the sense that all the relators are triangular. And how can I do this? I mean, all the relators are loops in the Cayley graph, so the only way to do it is to add generators. So that means that sort of to triangularize a presentation, you sort of have to add more and more generators. So for instance, I mean, if you're more familiar with the other model, the model in which you increase the length in the in the presentation? Well, I mean, the equivalent of that, if you want to take that thing and the length is more larger and larger, the length of this cycle, you can only do it by this splitting, which means that this time what is going to increase is the set of generators. So this is what explains how the triangular density model is constructed. It's one of the reasons, one of the things that explains this. In all both models, so both Gromov model and the triangular density model, you have to start with the density. So you have to start with a parameter between 0 and 1, and this parameter is going to measure how many relators you have compared to the number of generators. So here is how the model is described. So we consider formally a set of generators with m generators. M is the number that's going to increase. And this is going to represent our increasing of the sort of set of groups with finite presentations. And now, so we look at all the possible triangular relators. That means we look at all the words in S and its inverse, because we work formally, same as for the free group, of length 3 cyclically reduced, meaning this. So we're about to list all the possible words that could be relators. Essentially, this is a set of cardinality cube, the cube of M. And then we consider power D of this cardinality. Essentially, this is what we're doing here. So if we have that many possible relators, we consider the cardinality of that power D, so that means obviously strictly considerably less. And then we decree this is going to be the cardinality of the set of relations we work with. And then we look at all the possible choices, and we assume that all the possible choices are equally probable. And we choose them at random, and then the model is going to be the set of all the presentations of this form. So these are the elements that compose the model. And in fact, this is connected to one of the models of random graphs, so the Erdős-Renyi model of random graphs. And this is really very useful, in fact, when we're looking at the fixed point properties. And then the way we study this is that we let M go to infinity, and for each set, at each step M, if you're interested, if we're interested in a certain property, like P, at each step M, we count the number of groups with this presentation for M fixed satisfying P, and we look at the probability of that, and then we let M go to infinity, and we see how this probability behaves. And we're essentially I'm only going to discuss things that happen with overwhelming probabilities. So asymptotic almost surely, meaning the probability actually goes to 1. So this is the model that we consider. And as it will become apparent later, this is just the best possible model if you want to look at fixed point properties. So first of all, just looking at generic properties, if the density is too large, meaning that we considered too many relators compared to the number of generators, then the group is almost asymptotically, almost surely either trivial or Z2. This is Gromov who noticed that, because sort of Gromov introduced this in the realm of finitely presented groups, and most of the basic initial references are Jan Olivier's survey. For density less than a half, the group is asymptotically almost surely a Gromov hyperbolic and infinite. That's the most important, actually. And then for density larger than a third, the group has property T. So this is an initial in a paper of Zhuk, and it has been developed in a later paper of two brothers, Kotowski. And the basis of this is the following combination of facts. So it essentially is in the work of Garland, this whole idea, and it appears as a criterion in a paper of Banach and Shatkovsky. So one way of knowing if a group has property T is if we know that it acts on a simplicial complex, properly discontinuously and co-compactly, so therefore it is the fundamental group of the quotient of this simplicial complex. And the condition that we need to have on the simplicial complex is that the link of every vertex is a strong expander in the sense that the first non-zero eigenvalue of the Laplacian is larger than a half. So this also sort of gives perhaps a way of building groups with property T if we manage to build complexes that have this condition of the link, then the fundamental group is a group with property T. So this is how you can detect a group with property T, and this was combined with an older result of Friedman, because if we work with a random group, then the simplicial complex it works on, it's simply going to be the Cayley graph of this group in which we add a two-dimensional simplex for every relator. And the question is, for a random group, do we have this condition? And we do have it because for random groups, the link is a random graph, and random graphs are strong expanders in this sense. So this is what works.
Can I ask a question?
Yes.
Because these groups are groups where the number of generators and the number of relations is going to infinity and the lengths are fixed, right?
The generators,
Number
is fixed.
The number of the length of the relators is fixed, but the number of generators increases.
So the degree, if you think about, for example, Cayley graphs, the degree is going to infinity. So what kind of random graphs are these? I would think there would be more like.
About the random graphs, they are random graphs, so they are in the link to begin with.
So what is the degree of the random graphs? I'm confused about the relation between the random graph and the presentation of the group.
Well, I mean, they appear in the link, right? So you're looking at, so you consider the Cayley graph of the group, right?
Which has
And
degree going
for
to
the
infinity.
triangular presentation, it's just going to be a simplicial complex, right? And you just look at the length of every vertex, and this one is going to be the random graph that you consider. And so I think so. Normally, I think it's enough if you look at graphs of bounded degree. In fact, I don't think you need to increase the degree. I mean, yeah. I mean, the relation with the random graph theory it's the whole paper of Kotovsky and Kotovsky. So it's
Okay, so it shouldn't be obvious to us.
Well, it shouldn't be difficult.
Okay. But the Cayley graph has degree going to infinity, or am I misunderstanding this?
The Cayley graph has a degree going to infinity,
Okay.
yes, because you increase the number of generators.
Exactly.
Yes.
Exactly.
Yeah.
But doesn't translate to the degree of these links.
So well, it does actually.
So then I don't understand the relation with Friedman's theorem.
The link?
But this is the theorem. This is the theorem of Zook.
Okay.
So
It's okay.
it's not a pure combination of these two facts.
Okay.
It requires work both by him and actually also by Kotovsky and Kotovsky.
But in the list you mix two models. Maybe this is so there is a triangular model and also density model on the same.
Oh no! I'm talking only about the triangular model.
But then you have to. It's not only Gromov. You need to do some transformation.
No, for the triangular model is Gromov. For the triangular model is Gromov.
No, the results of phase transition is for density model. It's not. Then you need some transformation.
This is in Jan Olivier's survey, so I'd attribute it to Gromov.
For density model, not for triangular.
For the triangular as well. Okay, we can discuss.
The proof for the density and triangular models are basically identical, you just let a different parameter.
Yeah.
Yeah, but you need some transition. Okay, that
Like
doesn't matter. The results are true for triangular.
To add. I'm happy to add. Whom would you like to add next?
No, I don't want to add. Just to clarify that this is for triangular model use date.
Yes. I'm not stating it. You can ask Pierre, it's next to you. I think I'm attributing correctly.
No, my remark was not about
Yeah.
attribution. It was just which model you focus on triangular model.
I'm only talking about triangular model.
Okay.
So just the other one I'm just mentioning in case you have some, you'd like to connect to that. The connection is not clean, it's just one way. There's no equivalence. As you will see actually, for the next item, because this is not what happens in the Gromov density model. So in the triangular model, actually, a third is the threshold, and pretty much everything is known about this threshold. And actually, below the threshold, it's quite radical because random groups are free groups. So it's amenable in a very non-interesting way. While in the length model, as I'm sure those of you who are interested in that may be aware, things are still open. So there's no threshold. I think the proposed threshold by Piotr Petitsky is 1/4, and you, by John and Piotr Petitsky, is 1/4. So things are different. It's true, there's no clean, the sort of the triangular model, from the triangular model you can go to the length model by sort of some quotient procedure, which indeed explains why the property T goes from triangular to length, because property T is inherited by quotient, but not the same for amenability, so it's a different matter.
I think I'm missing something basic, and these groups have relations by definition. How can they be free groups?
Well, yes, but you just throw relations. In fact, so you throw relations, and in the end, you remain with a free group. You can do it.
These are not free generators, just.
Yeah, it's just not the free basis, obviously. Yeah.
I see.
Yeah, no, this is striking, but it's true. And also, things are known in 1/3. So at 1/3, it's the things coexist. But do you have any other questions? Okay. So now let's see what we can say for this for the fixed point property for LP spaces, the one that I mentioned. Right. So because that's sort of a source of examples where we can study this. So we fix our density between 1/3 and 1/2. So obviously, the fact that the group for this kind of density is infinite hyperbolic, this is Gromov. So it's not Oppenheim or McKay. Now here, so we're looking at this f of g, measuring the strength of the fixed point property. So measuring how big is that interval of fixed points. And now here, this inequality is due to John, and therefore this inequality as well. This is Oppenheim's great progress because it wasn't nobody managed to do it before him. This is also this is actually Marc Bourdon, because he says that above the conformal dimension you have proper actions even. But what is remarkable about this is that here we have basically by Lipschitz equivalence for generic groups between this f of g, measuring the fixed point property, the dimension and the dimension of the boundary, and they both grow at the rate, a logarithm rate. So there has been progress before that. To begin with, Piotr Nowak was the first to do something about random groups and a lower bound of this f of g. His bound, the method is really great and actually it could be generalized and stranger things could be obtained, but his bound, in fact, decreased to 2 as n increases. And further progress was obtained by us with John and by Tim Delatte and Michael de la Salle. So we obtained something like this, but there was also a factor, log of log, power, log of log of them. And Michael and Tim managed to remove that. And there's also something even better than looking. So I'm anticipating with this last bit, so I'll come back later. Because the work of Tim and Michael actually talks about fixed point properties of random groups in a larger class than just LP spaces. They consider the so-called uniformly curved Banach spaces. This is a subclass of the uniformly convex that you have seen in the talk before. It is a notion that was introduced by Gilles Pizier, and actually, remarkably, it contains all the known constructions of uniformly convex Banach spaces. So it is still an open question if there is an example of uniformly convex Banach space that is not uniformly curved. As I understand, people believe that very likely it does exist. But it's just to say that for all the uniformly convex Banach space we usually work with, like the LP, quotients, subspaces, interpolations, all the known procedures do give you uniformly curved things. So it's a really large class covering all the interesting examples. And the result of Tim and Michael showed that actually random groups with, let's say, with the same reformulation, if we look at the random group in this model depending on M, and then we look at the generic class of Banach spaces, the class of Banach spaces for which these generic groups have property, a fixed point property, this one increases as M increases, it becomes larger and larger. Well, the same phenomenon happens here actually. In the end, it covers the entire range of LP spaces until it covers everything, covers all the uniformly curved Banach spaces. So that means you can find hyperbolic groups with fixed point properties for any kind of uniformly curved Banach space. So that now is a large class of examples of groups for which measuring the strength of property T via this, or of A-terminability via this, becomes meaningful. The problem obviously is that it's large but non-explicit because it's probabilistic. But that's that. Can't tell everything. So, do you have any other questions?
Do the uniformly curved Banach space compare with the LPs, or?
LPs are uniformly curved. Yeah, as I said, like all the known examples of uniformly convex are uniformly curved. So what is open is, can you find a uniformly convex that is not uniformly curved? And very likely, it's going to be some sort of exotic example you wouldn't want to work with anyway. Or depending, I mean, maybe you would, I wouldn't, but it's a matter of taste. Okay, so do you have any other questions? Okay. So, right. So now we're looking at those parameters and those sets. So the set f of g, so the fixed point properties, the range of LP spaces for which we have the fixed point properties, and PG, the range for which we have a proper action. And well, I mean, we want to discuss this for groups for which both are non-empty. Well, I mean, we have to throw away all the higher rank lattices, and then the only other examples are rank 1 lattices and random groups, which are all hyperbolic. So it makes sense to discuss these questions for groups that are hyperbolic and with property T, because I mean, the fact that they are hyperbolic grant that this is always non-empty, and the have that property T implies that this is always non-empty. So for these groups, I mean, one can ask few questions. Well, we obviously have this inequality. Can we have equality? I actually don't know any example. I mean, we can cook up one, but you know, like natural. For instance, I don't know what happens for lattices. Then the second question also, oops, aha, sorry, this is f of g. Sorry, it's a misprint, so it's f of g. Again, following up on the previous theorem, since we have these inequalities between these parameters and the conformal dimension of the boundary, can we relate them to something geometrically significant? For instance, can we relate them with the conformal dimension of the boundary? So for instance, if the group is hyperbolic and with property T, can we say that either this parameter, the fixed point property one, or the proper actions one relates to this dimension of the boundary by a formula or a double inequality? Now, some of these questions, so there are a few things that are not known, but at least to one question one can answer, the fixed point property. The fixed point property does not relate, so you can make the gap between f of g and p of g as large as you want, and in particular the gap between f of g and the conformal dimension of g as large as you want. So given any integer, you can find a hyperbolic group for which the fixed point property stops at 10. And while the conformal dimension of the boundary can be as large as possible, and p of g as well, actually. And this is done using some trick from small cancellation, which is pretty, I mean, like as follows. If you are given a finitely presented group with the fixed point property, everything is hyperbolic here, actually, even if it's not written. If you have a finitely presented group with a certain property, and you have another hyperbolic group, you can construct a group G with property T, such that the finitely presented group is a quotient, and such that the other given group is a subgroup and even quasi-isometrically embedded. So you can embed this quasi-isometrically in something like this. So then that means that now you can see what we're going to do. We're just going to take P to be just a lattice of isometries of the quaternionic plane, which explains the 10. So this one, we know that it starts acting properly for P larger than 10. And we just take H as one of those hyperbolic groups with very large dimension of the conformal dimension, very large conformal dimension of the boundary, and who have like a very large range of fixed point properties. So that means that before we hit that range, the group G can't act properly. But it has to stop having property T at 10 because it's inherited by quotient. So it's just like a trick from small cancellation that allows to do this. Nevertheless, it remains a fact that generic hyperbolic groups do satisfy this inequality. And this is like a sort of a small cancellation group, sort of built for the purpose. It is not a generic case. So one might think that if one puts a certain assumption that will capture the generic hyperbolic groups, you'd be able to say that for that large subclass of hyperbolic groups, we do have this comparison, and we do have this by Lipschitz equivalence between fixed point property parameter, conformal dimension, and P of G. But that's a question. And then it remains to look at the second parameter, the parameter measuring the strength of a terminability. I mean, we know that it's related by an inequality, but is it related by more than an inequality, by a double inequality of a certain kind? So that's not known. And, right. So this is how things stand for the LP spaces. And now if one moves to sort of like a larger set of Banach spaces, as the result of Tim Delat and Michael de la Salle invited us to, why don't we consider all the Banach spaces for which the group has the fixed point property, as the group is from now on, let's say, countable and most of the time finitely generated. We're going to restrict to separable Banach spaces, and for those we have a topology. So it's a set and it's endowed with a topology. So that would be a reasonable, this would be like really the best kind of spectrum, right? So you don't miss out on any fixed point property that the group may have. For some reason related to the topology introduced by Mikhail, it is best to consider, and actually for many reasons, it is best to consider the set of all the separable Banach spaces for which the group has a fixed point, but sort of the largest set that is also closed with respect to taking subspaces, alter limits, and L2 finite sums. So for subspaces and alter limits, the justification is in the topology. I mean, you sort of want that set to be topologically reasonable. For the L2 finite sum, the reason is one does not want to have a fixed point property for silly reasons of the kind a certain interesting Banach space has a very small group of isometries. So for that reason, well, I mean, if it does happen that you look at such a space, you can consider this space instead with a geometry similar to the first, but a much larger group of isometries, and check if that one, if you have a fixed point property for that one. Right. So, and if we add this, so if this is the spectrum that we're looking at, the largest set of separable Banach spaces for which the group has a fixed point property, stable with respect to considering spaces, alter limits, and L2 finite sum, then there is an old result of Fernandez showing that all such spaces can be defined by a certain inequality, which is very similar to the inequality defined uniform curvedness introduced by Gilles Pizier. So let me tell you a few things about this inequality, and probably it becomes apparent by now that this part of the talk should be given by Mikhail, but he is an organizer, so he can't give me a talk. So I'm a geometric group theorist. So I'm going to answer as much as I can, and for the other things, I refer you to Mikhail. But anyway, so this is what we're looking at, and here is how we're going to proceed to actually define our spectrum. So first of all, we're going to look at the Banach spaces, which for the moment we call Markov convex, and perhaps we're going to keep this terminology in the end. So here's what the definition of a Markov convex space is. One just wants the following thing. Essentially, one wants that let's look at the definition actually. So if we have a finite graph, well, we endow it as usual with the stationary probability measure for the random walk. I mean the usual one. And Markov convex means the following thing. We're looking at the norm of the Markov operator of this graph. Again, I changed G to gamma. I'm really sorry, because you probably have seen, I was supposed to use G for groups and gamma for graphs, but I forgot to change everywhere. So here G is equal to gamma. And the condition, so we're looking at the following condition. So if the norm of the Markov operator is at most epsilon for this graph, then for this corresponding space, we want it to be controlled by a function like that, and we want this, so L to 0 just simply means that we're looking at the sort of orthogonal over the constant functions. So we look at square integrable functions, and what we want is that this function goes to 0. So what we really want from this space is that whenever we have a graph with a certain control on the Markov operator, we want the operator, the Markov operator corresponding to functions with target x, also to have controlled norm. And we want this norm to go to 0 as epsilon goes to 0. So this is the condition. And let me tell you a few properties. I mean, like one of them is precisely that this is an a priori larger class than the class of uniformly curved Banach spaces. So uniformly curved implies this. But this one is more geometric, and this one is more clearly connected to the fixed point properties. Another thing that is quite clear is that expander graphs are also expanding with respect to this class. So in fact, this is somehow it's tailored for the purpose. It's going to keep expansion. So spaces that are Markov convex for spaces that are Markov convex, the expansion in the classical case will imply the expansion in this case. And in particular, the random group property of Tim Telat and Michael de la Salle is actually translated to this class as well. So,
can you say again, what is this A gamma X?
It's the Markov operator. I mean, you average, so you look at functions, right? So it's the usual Markov operator means that you average. Here you look at functions from your graph, actually from gamma 0 to your space. And the previous Markov operator, you're averaging the neighbors on the neighbors in the, like for functions over R, or equivalently, the target is Hilbert. And here you average for this kind of functions. And that's going to give you. And you're just looking at the norm of this operator, A gamma G, A gamma X. And you want this, the norm of this operator, to be at most delta X of epsilon for any graph for which you know that when you put R here, you get the bound epsilon. So if you have contraction for the classical Markov, you're going to have contraction for this. So the remarkable thing is that actually, like all the uniformly curved Banach spaces are like that. And again, the randomness statement that I mentioned before actually applies to this. If you look at the hyperbolic groups in the triangular random model, and M goes to infinity, and you look at the range of Markov convex spaces for which these groups have the fixed point property, this is going to keep increasing until it covers the whole class. That's Tim Delat and Michael de la Salle. Right? It's a really nice condition. I mean, it's a sort of a natural condition. It refers strongly to expansion, in my view, and this is actually what made in fact, with what I mentioned until now, you can see why this is true, because actually, what one can say, it's more. I mentioned this old result of Friedman that generic graphs are expanders with the first non-zero eigenvalues larger than a half. But then you can say that random graphs are expanders that are stronger and stronger, meaning that the lower bound of the first non-zero eigenvalues grows to 1, or also meaning that the norm of the Markov operator decreases to 0, which means that as you let M increase, the Markov operator of the corresponding graphs in those links are going to have a norm that decreases to 0, but then that means that the same thing will happen. So if the links here are expanders, strong expanders, meaning that the lambda 1 is going to be a 1 minus, I don't know, epsilon prime, then that means that for the same links, the Markov operators have smaller and smaller norms. And therefore, the Markov operators with targets in this set have smaller and smaller norms. And that's what explains that in the end, you end up having a fixed point property for any Markov convex space. That's it, actually. There's nothing more. It's a sort of a stronger version of Friedman, which is done by, I forgot whom, it's a combinatorist, and plus the actual definition, which is really tailor-made for this to work. Right, so let's go to the spectrum. This is how the spectrum looks. So you see, in the end, it's not so bad, because it's just two numbers. So we are looking at all the fixed point. So at all the fixed point properties for spaces for which this Markov modulus is controlled in this way. So it's a strip, in fact. So it's like this. And C equals to 1, and so theta, so this is theta, and this is C. And the Hilbert spaces are here. And if you consider, so this is how you define the spectrum. We look at the group G, and for each of these values, we check if this group has if the group has a fixed point property for all the Markov convex spaces where the Markov modulus satisfies this inequality. Now, if this is how you define this set of Banach spaces, it's going to be stable by duality as well. And it is going to be stable in all the ways that we mentioned before. It's going to be stable by quotients, by subspaces, and by L2 direct sums, and by ultra limits, and complex interpolation. So, and as I said before, this is actually justified, this way of proceeding is justified by the approach the other way. So if you look at all the Banach spaces for which the group has a fixed point property and you ask that it's closed, this old result of Hernandez tells you that they're going to be characterized by an inequality like that anyway. So it's not very unnatural. It's a good way of looking at the fixed point properties. And now let me tell you what the features of this set are. First of all, it is open for the reasons that I mentioned. All the fixed point property is an open set, and therefore, in any possible sense of the way, you're always going to get that any spectrum characterizing the fixed point is open. Then the other thing is that, well, I mean, obviously, if you have this property for a certain C and theta, you also have it if the modulus is even smaller. So that essentially means that in this strip, S of G is about a non-decreasing grad continuous. So it's going to be like this. It doesn't look non-decreasing, but imagine that it's non-decreasing. Now, if you look at the intersection with one, in fact, this is just about this inequality. If you look at what happens on one line, so that means for a certain theta, you always work with spaces with control type and cotype if you're interested in this sort of thing. And this is what I said before. If we look at in fact random groups, in the end, the spectra of the random groups, random hyperbolic groups, is going to cover the entire strip. So here are two things that one can say that are interesting about this spectrum, besides the fact that it's somehow the closest that one can get reasonably of a sort of a like full range spectrum. So we just take all the Banach spaces for which you have the fixed point. The first one, it has an interesting connection with the Shalom conjecture. So I'm going out of time. I'll just like sort of quickly remind you about this. So as I understand, Ian's talk was about that. So the Shalom conjecture is about another possible strengthening of property T, which is that the previous strengthening was we're looking at affine isometric actions, but instead of Hilbert we put Banach. Now here we look at affine actions on Hilbert spaces, maybe also on Banach spaces, but what we allow is we allow for the unitary part to be uniformly bounded. So that is our action is going to be, well, it has a linear part, and it has a translation part, which is a co-cycle, and for an isometry, this is a unitary representation. And now here, we just say that this is uniformly bounded. So all these are bounded operators, and there is a common upper bound. And like unsurprisingly, so again, and we can formulate property T in the same way. If we have an action in this manner for Hilbert spaces, do we again have the fixed point property? And higher rank lattices actually still have the fixed point property even for affine uniform Lipschitz actions, not just for Hilbert, but also for LP. It can be deduced, or maybe it's even, it can be deduced from work of Badea, Fuhrman, Gerlander, and Monod. And like following the same idea, this is yet another strengthening of property T. Hyperbolic spaces should lose it. And this is what the conjecture of Shalom is. Hyperbolic groups, and here obviously we're interested not in eta-minimal groups, we're interested in groups with property T, should start acting properly if we allow for this kind of actions, affine uniformly Lipschitz instead of just isometric affine. For the moment, there is also a weaker version, actually. So let's say we don't want to prove that every hyperbolic group has a proper action. We just want to prove that every hyperbolic group has an action with unbounded orbits on a Hilbert space. And for both, there is only one progress that I know of, which is the theorem of Nishikawa, confirming this for lattices of isometries in the quaternion case. And actually, in that case, he proves a strong conjecture. He proves that these have a proper action on a Hilbert space. Other than that, nothing is known, neither for the weaker version nor for the stronger version, which is frustrating. And now, how does this relate to our spectrum? Because the weak Shalom conjecture is equivalent to the fact that the spectrum has always a compact closure for hyperbolic groups. So you can see it, yeah. So here is one thing that you can see in this spectrum. Do you have any questions? Stop thinking of lunch. Because the big Shalom conjecture is much more meaningful than lunch. I don't think so.
For the what?
For the Octonian,
Yes.
it is?
It's in the paper by Ignacio.
Oh, I see. So, oh, right. Oh, sorry. So that you should have corrected me actually. Okay. So it's also known in that case. So, yeah. But right. So that's one thing. Do you have any other questions? Okay. So then the last bit is that. It's in fact actually, that's it. This is my last slide. And it says the following thing. First of all, every finitely presented group with a spectrum contained in the spectrum of a non-elementary hyperbolic group actually has the exact same spectrum as the spectrum of a non-elementary hyperbolic group. In particular, the only possible spectra with compact closure must come from a hyperbolic group, because of this construction. So the spectra that are relatively compact can only come from hyperbolic groups. But then, of course, for the others, we don't know anything, and I'm going to stop here. Sorry.